Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to give an example of application of the work energy theorem. So in this problem we've got these two masses tied together, this 30 kilogram mass and this 20 kilogram mass, and they're connected by a rope which goes over this pulley. We're going to try to calculate the time required for this 20 kilogram mass to hit the floor here. In this problem we're going to assume that friction is not an issue, so we're going to assume that's a frictionless surface. And we're going to at least start the problem by using principles of work and energy. So I'm going to start by noting that there's two different masses. So I'm going to go ahead and give them names. I'm going to call this one mass A and this one mass B. Now, mass A is going to accelerate down at some value, not g, something smaller than that. I'm going to do these dots here, my motion diagram, to kind of indicate that that mass A is speeding up. Here's kind of a snapshot of mass A right before it hits the ground. It's got a velocity vector down that I'm going to call v2. And while I'm at it, I'm going to go ahead and call this position 2. Right? I'm going to come back up here and call that position 1. Right? Now I'm going to focus on mass B. This is what I'm going to call position 1. Mass B will be accelerating to the left. Here's a picture of mass B at position 2 after it's traveled a distance of 2 meters. Right. At this position, mass B will have a velocity to the left, and I'm going to call that v2. Important to realize that the speed of this mass A and the speed of mass B are going to be the same because they're connected by a rope that's not changing in length. Next step, I'm going to go ahead and write out the work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2. Now, when dealing with potential energies, we always have to define a datum. I'm going to go ahead and do that. I'm going to draw this in blue, red. So that's going to be my datum for this problem. Now, with that choice of datum, go ahead and label that. The PE2 term for mass A is going to be 0. The PE1 term is going to be an MGH term where the h is this height, 2 meters. Now let's talk about mass B for a moment. The PE1 term would be MGH, the h would be that distance right there. The PE2 term would be another MGH, which is going to be that distance, and the h will be that distance right there. You'll notice that it's the same mass, gravitational constant's not changing within that problem, and it's the same height. So those potential energy terms are the same. So no matter what I put for PE1 for mass B, I'm going to have exactly the same thing under the PE2 term, and they're just going to subtract off anyway. So long story short, if something's not changing in potential energy, you don't need to worry about it. All right, so the PE1 term is going to equal MGH, but that mass is mass A, the 20 kilogram mass. The system starts from rest, so the kinetic energy term is 0. I'm not going to worry about that. As usual, I'm going to do the work term last. I'm going to jump to the PE2 term. All right, PE2. Right, mass A is at our datum, so it does not have a potential energy. And I've already talked about why we don't need to consider mass B. It's not changing in potential energy, so we can go ahead and put a 0 there. And then KE2, there's an important part of this problem. Because I'm defining my system as both masses together, let me kind of demonstrate what I'm talking about. This is my system here. Because of how I'm defining my system, I need two kinetic energies. I need one for mass A, right, a 1/2 mv squared, but that m is mass A, and the v is the one I called v2. And I need another kinetic energy term for mass B, 1/2 mass B times v2 squared. So I need two kinetic energies, and that's a consequence of how I'm defining my system. I'll come back to that here in a few minutes. All right, the work term. So because of how I'm defining my system, if I look at forces acting on the system, I'm going to draw those in red. We're going to have a gravitational force right here in mg. We're going to have a gravitational force here, another mg term, a normal force here. There's also a pulley force, or some sort of force acting on the string here at this point. These are all the external forces acting on my system. And I'm going to go through them one at a time. This force is in fact doing work, but I'm taking that into account with this potential energy, so I don't need to do anything about that. The mg on this part of the system is not doing any work because it makes a right angle to the velocity. Same thing with the normal force. So there's no work term for either of these two forces. This force, this capital F force here, the force that the pulley exerts on this rope, there's no work term for that because the pulley's not moving. If this puller were to somehow like move over to here at the same, while this was happening, we would need a work term for it, but it's not. So there's no work term for this force because there's no displacement for it. So I've considered all of the external forces on the system. There are none doing work, so I'm going to go ahead and get rid of them now. And therefore the net work is 0 on the system. Now, it's important to realize that's a consequence of how I define my system. I define my system in such a way that the tension acting on this mass right here is an internal force. If we look at that tension, it's acting that way on mass A, and it's acting to the left on mass B. If I wrote a work energy equation where this was my system, it would only have one kinetic energy term, but I would have to include a work term for that tension. If I wrote a work energy equation for only this mass, right, it would only have one kinetic energy term, but I would have to include a work term for that tension. Now here's a very important thing to realize. If this mass moves 2 meters, the work done by this force is going to equal positive t times 2 meters. The work would be positive because the tension is in the direction of the velocity. The work done by this tension is equal to minus t times 2 meters. Same tension, if this pulley is very small or has a very small mass compared to the rest of the system, same 2 meters, but the work would be negative because the tension vector points up, but this thing's velocity points down. Notice that the net work on the system is 0. So that's the advantage of defining the system the way I have it. The tension is an internal force to that system. It's not doing any net work on the system, so it doesn't really come into play. But I have to have 2 kinetic energy terms. Oops, guess I can't get rid of that last one there. Go ahead and I got to erase this force vector. I don't need it anymore. Okay, so 2 kinetic energy terms, that's a consequence of how I define my system, and I did that so that I didn't have to mess around with these tensions. Net work 0. Only thing left to do is put in numerical values. So what we're going to have is m sub a gh equals 1/2 mass A v2 squared plus 1/2 mass B v2 squared. I'm going to go ahead and put numerical values into this. So this thing right here is going to be 20 times 9.8 times 2. And I'm going to put my NCU here because I don't feel like going through and writing units everywhere. That's going to equal, all right, 1/2 MaV2 squared. Now mass A is 20. 1/2 of that would be 10 V2 squared plus. Right? Mass B is 30. 1/2 of that would be 15 V2 squared. I'm going to take a moment here and just calculate a numerical value. Right. So this reads 392 equals 25 V squared. That's V2 squared. If I go ahead and solve that for V2, let's see what I get out of that. I get 3.96, and I'm just going to call that approximately 4 meters per second. So V2 is going to hit the ground at about 4 meters per second. It's important to note that the difference between average and instantaneous velocity. In this problem, that's an instantaneous velocity. It's the final velocity. It's the instantaneous velocity when this mass hits the ground. All right, the next part of this problem, I want to try to relate that to time. In order to do that, I'm going to now study kind of the motion of the problem. So what I'm going to do here is I'm going to draw a velocity graph. Give myself a little room. Now, when we're going to study the velocity of a system, we need a coordinate system to do that. So I'm going to go ahead and study this. I'm going to put a coordinate system here pointing down. So that's going to be my positive x direction. I could also come here and put a coordinate system here and point it this way. Plus x would be perfectly fine. So at t equals 0, this object is at my x equals 0. Its velocity is going to increase linearly. Now hopefully we've seen enough Newton's second law examples to know why. We're going to have a constant force on this, therefore the acceleration is constant. So this graph is going to give me a linear velocity curve. So it's going to look maybe something like this. Out to the time when it hits the ground, which I don't know. I'm just going to call that t. But what I do know is that the final velocity when it hits the ground is 4 meters per second. So I can label that on my graph. Right? Now another thing I know is I know that this mass is going to accelerate down and cover a distance of 2 meters. So in the context of my motion study, I'm going to call that a delta x, a change in x, because I called this plus x pointing down. And I know that that change in x is 2 meters. And then the million-dollar question is, how does that relate to the graph? And the answer is by that area. The area under your velocity curve gives you the change in position, which allows me to write a real short equation here. 1/2 t times 4 meters per second is equal to 2 meters. And that's a pretty easy equation to solve. I get t equals 1 second. And while I'm at it, we can also calculate the acceleration of mass A. Now that I have the velocity curve listed, nailed down, the acceleration is the slope of your velocity, or it's delta v over delta t. In this example, that's going to be 4 meters per second over 1 second, or in other words, 4 meters per second squared. So that's pretty well it, I think, for this example. I just wanted to go through one that demonstrated how to write a work energy equation for a system that's kind of tied together like this, that has two parts. In this example, it didn't have any friction. I'll go ahead and work this again here and take a look at what it would look like with friction. And another important part of this problem is how to take this thing that we calculated, this final velocity, and use it in the motion study of the problem to do things like calculate a time and tell us the acceleration of the system. So, hope this video helps demonstrate these things. Have a great day.